Bo día, benvidos ao 26º Encontro Galego Portugués de Química. Permítanme que lles presente os acompañantes na mesa. A miña dereita está a coordinadora do Centenario Estudos de Química, doña Pilar Bermejo Barrera. A continuación está o decano do Colexio Oficial de Químicos de Galicia, Manuel Rodríguez Méndez. A miña esquerda está o presidente da Sociedade Portuguesa de Química, Artur Manuel Suárez da Silva, e, finalmente, á esquerda está un membro da sociedade e representante da delegación de Porto, da Sociedade Portuguesa de Química, decía, o profesor Víctor Armando Pereira Freitas. Ben, neste ano 2022 celébranse os 100 anos de oferta ininterrumpida de estudos de química na nosa universidade, e, polo tanto, unha ocasión singular, e nesta ocasión singular acollemos o Encontro Galego Portugués de Química, o que lle dá un brillo especial á nosa conmemoración. Agradecemos, por tanto, tanto a Sociedade Portuguesa de Química como o Colexio de Decanos que elixiran esta sede para facela coincidir con o noso centenario. Bueno, desde 1985, a mediados de novembro, os investigadores e profesionais da química e da enxeñería química temos unha cita que se vai celebrando de forma alterna entre Portugal e España. O certo é que esta é unha oportunidade única para establecer lazos e colaboracións entre os profesionais e académicos que temos interese común en certas áreas. De maneira que, de novo, este é un motivo de agradecemento para os membros de ambas sociedades. Eu non teño máis que dicir, máis que a continuación ceder a palabra a dona Pilar Bermejo Barrera como coordinadora do centenario.
Moitas gracias, señor decano da Facultade de Química. Bueno, en realidade eu non vou a decir moito máis que o que dixo o meu colega, porque é un orgullo para a nosa facultade, para a nosa universidade, poder celebrar aquí esta 26ª edición do Encontro Galego Portugués de Química, porque, ademais, tal como di no prólogo do libro que escribeu o decano do Colexio Oficial de Químicos, é que a primeira edición deste encontro celebrouse tamén nesta facultade. Para nós, 100 anos son moitos anos, é moi importante a súa celebración, porque antes desos 100 anos, antes do ano 22, en Galicia non había unha enseñanza da química como tal, solamente había algunhas disciplinas, curiosamente, nas facultades de farmacia e de medicina. Había unha grande demanda por parte da propia USC, pero tamén por parte da sociedade galega para a implantación dos estudios de química en Galicia, porque Galicia, o desenvolvemento das empresas relacionadas coa química era moi escaso, mentras que en outras comunidades autónomas, evidentemente, había unha evolución moito maior. Por tanto, había unha grande demanda. A química que empezou a impartirse como licenciatura de química nesta universidade, evidentemente, despois expandiuse para as outras cidades de Galicia, e se crearon as novas universidades. Por tanto, celebrar 100 anos é sempre importante para recordar de onde venimos, tomar nota e aprender para a onde vamos. Enhoraboa aos organizadores desta nova edición, porque creo que ten un importante número de asistentes, e, de novo, agradecer que escolleran a nosa facultade para a organización deste congreso. Moitas gracias.
Gracias. Ten a continuación a palabra o profesor Víctor Armando Pereira Freitas.
Muito obrigado. Portanto, eu vou começar por cumprimentar a mesa. Queria cumprimentar o Dom Gil Samartã, diretor da Faculdade de Química, a quem agradeço, enfim, a possibilidade de organizar este encontro na Universidade. Portanto, é sempre uma referência e algo que é desejável para um encontro de Química, não é? Queria também cumprimentar a dona Pilar Bermejo, que é a coordenadora do centenário da Universidade, a quem também, enfim, dou os parabéns à Universidade pelos 100 anos, e a quem endereço os meus cumprimentos. Ao meu colega Artur Silva, presidente da SPQ, da Sociedade Portuguesa de Química, E deixei para o último ao Manuel Rodrigues, que é o decano do Colégio de Química, a quem agradeço publicamente os meus cumprimentos e quem lhe dou os parabéns pela organização deste evento. É muito complicado a organização de um congresso com estas dimensões. De facto, é um congresso que tem muita gente inscrita, cerca de 450 participantes, de que eu me lembro talvez seja dos congressos que mais gente tem inscrita. Portanto, não é fácil organizar um congresso a este nível. Portanto, eu estou aqui a falar na qualidade de presidente da delegação do Porto da Sociedade Portuguesa de Química e certamente muitos de vocês já sabem que este encontro, neste caso o galego ou português, porque é organizado na Galiza, em Portugal é o luso-galego, portanto há uma alteração de nomenclatura, mas trata-se exatamente do mesmo encontro, porque é um encontro que é organizado conjunto entre a SPQ, a Delegação do Porto, e o Colégio de Química da Galiza. Portanto, já vamos no 26º, portanto, o que significa que já passaram muitos anos, o interregno, entretanto, entre alguns congressos, significa que já andamos nisto há mais de 30 anos, e digamos que tem sido sempre um sucesso a organização destes congressos. É uma oportunidade para os mais jovens, os jovens dos mais jovens, os menos jovens e os outros também poderem participar e apresentarem alguns resultados da investigação que têm vindo a desenvolver. Para muitos de vocês, certamente é a primeira vez que fazem uma apresentação em público dos resultados e este tem sido um bocado a alma deste congresso. Portanto, nós pretendemos efetivamente manter este espírito dentro do congresso. E por último, enfim, vocês sabem que isto é um congresso especial, é um congresso que tem homenagem ao professor Costa Lima, uma pessoa que nos é muito querida e sempre foi, digamos, o timoneiro deste congresso, portanto, uma pessoa que esteve sempre presente. Eu não vou falar muito dele, teremos uma homenagem na quinta-feira, portanto, isso deixa-me particularmente agradado saber que a memória dele vai perdurar, pelo menos, entre nós. E termino desejando-vos felicidade, que corra muito bem, que façam network, colaborem entre vocês, discutem resultados entre vocês e outras coisas, partilhem o conhecimento, que é o objetivo deste encontro. Portanto, muito obrigado por estarem presentes.
A continuación a palabra Artur Manuel Suárez da Silva.
Bom dia a todos. Espero que tenham feito boas viagens, apesar da chuva que está. Por isso, aos que já cá estão é mais fácil. Aos que vieram mais longe, tanto de Portugal como de Espanha, que tenham feito boa viagem e que não estejam muito molhados. Pronto, é o que se espera para começar este dia. Bom, segunda palavra para cumprimentar realmente as pessoas também como o Vítor, que estão aqui na mesa, e agradecer. Por isso, ao Dom Jesus a São Martim, ao decano desta faculdade, por nos receber aqui. É sempre bom organizar o congresso numa casa com muita história e muita tradição em Química, e por isso receber aqui este congresso, nesta data também, como a Dona Pilar Bermejo, já coordenadora do Centenário de Estudos de Química, também já referiu. Por isso, uma casa que se faz Química, onde já passámos e regressamos outra vez. E também olhando para esta audiência, como o Vítor diz, ou seja, temos muitos jovens, aqueles que continuamos a querer que seja um palco principal para eles poderem fazer as suas apresentações, tal como nós, alguns que estamos aqui na mesa também, de certeza que será a vossa primeira apresentação de quando entra nesta carreira, digamos assim. Muitos congressos não têm esta possibilidade e este dá-vos essa possibilidade de termos comunicações orais e que neste ano e neste congresso ultrapassam as 200, por isso é bem evidente daquilo que vocês vão ter ao longo destes dias. Por isso, agradecer então à faculdade e ao seu decano, cumprimentar a Pilar, como disse há bocadinho, porque também celebrar os 100 anos nesta casa é sempre bom, porque nós devemos celebrar a Química, a ciência em particular, mas a Química, porque nós somos químicos, e por vezes a Química é às vezes maltratada, e por isso nós devemos sempre aproveitar para celebrarmos a Química e para trazermos, pô-lo no foco, nos telediários, nos jornais, não só nas comunicações científicas, mas também na vida normal, para não ouvirmos depois nos telejornais dizer os químicos, e os químicos não são os químicos, são os compostos químicos, e eles referiram os químicos. por isso a ver se damos algum ensinamento também para a sociedade. Bom, por último, cumprimentar e agradecer ao decano do Colégio dos Químicos e ao Vítor Freitas, presidente da delegação do Porto, que é neste seio que são organizados estes congressos e onde eu tenho tido o prazer de estar ao longo dos anos, porque é algo importante que nós temos, é algo que nós eu diria que este congresso é e sempre será de uma família, e esta família é mais reservada, embora nós tenhamos alargado muito as fronteiras, mas é sempre bom, e com o número de participantes que temos desta vez, que já foi referido aqui, ultrapassando as 400, acho que é muito bom. Logicamente que depois de 3 anos que nós estivemos quase fechados em casa, na verdade, agora já dos últimos 6 meses já começamos a sair de casa, e este também é uma forma de nós dizer que precisamos de discutir os nossos resultados, de mostrar aquilo que nós temos, e discutir ciência mesmo, é estar frente a frente, não é estar atrás de um ecrã. Logicamente que o Zoom, ou o Teams, ou outras, qualquer plataforma, nos deu muita possibilidade de fazermos reuniões internacionais, de trazermos outras pessoas, mas eu acho que discutir ciência ainda continua a ser assim, frente a frente, onde nós fazemos as colaborações, como o Vítor dizia, fazer networking. Networking não é só estar em frente aos postas, às vezes é no coffee break que nós fazemos o networking, que nós começamos uma nova colaboração, e por isso acho que devem aproveitar este encontro, estes dias que vão estar aqui, e por isso se tiver chuva ainda melhor, porque as pessoas vão estar mais junto aos posters e a discutir e a fazer ciência. Acho que é assim esta forma de o fazer. Por isso, espero que os dias sejam frutíferos. O programa é muito interessante. Infelizmente não vou poder estar, mas terei pena de não assistir. E por isso queria dar também, por último, uma nota, uma vez que não vou estar na homenagem, mas não podia deixar de referir aqui o nosso pioneiro, o nosso bem-amado José Luís Costa Lima, porque é o primeiro encontro em que vai ocorrer sem a sua presença física, e por isso acho que é uma homenagem que é merecida de todos nós e de todos aqueles que ao longo da vida têm compartilhado com ele, ou compartilharam com ele, este gosto e este amor pela química e pelos encontros luso-galegos. E se me permitem, por grande protocolo, eu ia-vos pedir uma salva de palmas para o José Luís Costa Lima. Agradeço então, desejo um bom congresso para todos e que no final destes dias nos sentimos mais ricos por termos aprendido, por mostrado o que nós fizemos, e no próximo ano continuaremos juntos num congresso no outro lado da fronteira, mas apresentando o melhor que nós temos. Obrigado a todos.
Moitas gracias, profesor Suárez. Finaliza esta ronda de intervencións don Manuel Rodríguez Méndez, decano do Colexio Oficial de Químicos de Galicia.
Bo día, buenos días, estimado señor decano, profesor Artur Silva, profesora Pilar Bermejo y compañero de mesa también, Víctor Freitas. Señoras y señores, muchas gracias por estar aquí en este Encontro Galego-Portugués. El año 2019 celebramos en Santiago la 25ª edición del Encontro Galego-Portugués de Química. El parón obligado por la COVID-19 nos ha privado de vernos en los 2 sucesivos años, pero este año retomamos el encuentro donde lo dejamos, aquí en Santiago, con la mayor ilusión que podemos tener. Atrás quedan 2 anos complicados, algunos perdemos amigos e familiares pola COVID. Para todos eles e para todas as persoas que están sufrindo a guerra de Ucraína, a nosa solidaridade e o noso cariño para todos. O ano pasado, o encontro, todos nós sufrimos unha perda importante, a perda dunha persoa entrañable para todos. Refírome ao profesor Costa Lima, que faleceu o ano pasado e que queremos render homenaxe nesta 26ª edición. O profesor foi unha desas persoas que impulsou estes encontros desde a súa fundación, facendo que estes mantiveran o mesmo espírito co que se crearon alá polos anos 1980. A súa profesionalidade, o seu carácter amigable e conciliador permanecerá sempre na nosa memoria. Estou seguro que hoxe está véndonos, estea onde estea, e estará pendente de como vai este encontro. Así que, moitas grazas, profesor Costa Lima. Este ano, en recordo del, organizamos este congreso nesta fermosa cidade de Santiago de Compostela, ano santo xubilar, e tamén esta facultade dentro dos actos da celebración do centenario dos estudios de ciencias e de química, que tanto amamos e donde naceron os encontros. Non quero estenderme máis e quero, como digo sempre, que faledes vos cos vosos traballos, nas ponencias, nos pósters. Solamente quédame agradecer a organización, a todos os compañeiros que me axudaron que estuvemos organizando este encontro, tanto pola Sociedade Portuguesa de Química como polo Colexio da Asociación de Químicos de Galicia. A Facultade de Química, o seu decano, e a Pilar Bermexo, por todas as facilidades que nos deron para poder facer aquí este encontro onde naceron os encontros. Agradecer tamén o programa Conciencia, a colaboración con que vemos traballando nestes 2 últimos anos, e benvidos e benvidas pola nosa parte. Moitas grazas.
Moitas gracias. Con esta intervención remata a sesión de apertura. A min tan só me resta agradecer a todos a vosa presencia aquí e desexarvos que disfrutedes o máximo posible da nosa cidade. A continuación, don Manuel vai a darnos unhas palabras máis.
Solamente explicar como a logística de todo isto. Hai 4 salas, esta primeira, temos 2 salas neste mismo andar, 2 salas nos laterales, temos unha 4ª sala que está no segundo andar, a aula de química xeral, química técnica, química física, esta aula. Os pósters, planta segunda, planta terceira, poden estar desde o principio ao fin do póster. Abaixo hai unha cafetería, por se queredes tomar un café. Habrá o coffee break, cando toque, estará na terceira planta. Despois, os aseos, por se alguén necesita, nos laterais, entrando nos departamentos, hai cadro eléctrico, e despois vai haber os aseos. Non os equivoquedes, non vallades os cadros eléctricos, pode ser perigoso. E que despois, para xantar, hai por aquí, polo campus, no pendrive, onde tedes os resúmenes, tedes aí todo os sitios onde podedes xantar. De acordo? Por a miña parte, benvidos e que empece o congreso. Damos paso.
Sí, moitas gracias. A continuación ten a palabra o profesor Andrade García, do Departamento de Química Analítica da Facultade de Ciencias da UDC, para que nos faga unha revisión bibliográfica do premio Nobel do 2019.
Buenos días, bon dia, good morning. First of all, please let me introduce one of the most famous persons nowadays in chemistry, which is Professor Dr. Stanley Whittingham. On behalf of the organizing committee of this international conference, I would like to thank you very much his very, very, very kind attention of our request for opening this conference. He was really, really charmed and really, really gentle. So thank you very much, Dr. Whittingham. Ladies and gentlemen, my task here is quite difficult because I have to resume in several minutes the whole life of one of the most remarkable figures nowadays in chemistry, which is Dr. Whittingham. So before starting, I beg your pardon, and also from Professor Whittingham, because probably I will not be able to resume the very, very many accomplishments that he obtained in industry and in academia. And I think that it's very, very important to underline that he worked in both worlds, and they really are possible. It's possible to combine them. Okay, Dr. Whittingham was born in 1941 in Nottingham in England, and his father was a civil engineer and his mother was a chemist. And maybe this is important because his brother is also a PhD chemist and his niece is also a PhD chemist from Cambridge. So there is something in the family. And he also enjoys two sisters, I think. He attended Stanford School in Stanford, which is on the road from London to Edinburgh. And he got attracted to science thanks to the teaching of two professors, Mayor Lamb and Squeeze Bowman, in chemistry and physics, respectively. But he was also interested in the school not only in chemistry and physics, but also in sailing, in playing tennis, and in growing cacti. And in fact, nowadays, he still continues to cooperate actively with the Desert Botanical Garden in Phoenix, in Arizona. In 1960, he entered Oxford University to study chemistry, and his key tutor, Peter Dickens, attracted him to solid-state chemistry, and he also took classes on metallurgy. And by those times, the US Air Force Office of Scientific Research in London supported his undergraduate research on the recombination kinetics of oxygen atoms on the tungsten oxide bronzes. This first work resulted in his first publication in the Transactions of the Faraday Society. He got his PhD in 1968 and then won a scholarship to study catalysts to convert coal gas to natural gas. But suddenly, the UK discovered huge amounts of natural gas in the North Sea, so he had to change to study the reduction by hydrogen of the tungsten bronzes and a range of tungsten oxides, and discovered how the fast ionic mobility of the alkali ions dictated the reduction reaction pathway. In 1968, he moved to the Materials Center at Stanford University in California to work with Robert Huggins. Then his supervisor had to move to Washington, D.C., and Dr. Whittingham became de facto the leader of the group for 2 years. They studied the fast ion transport of alkali ions in the recently discovered beta alumina materials using the mixing conducting tungsten bronzes as electrodes. As a result of that work, he received the Jan Otto Award of the Electrochemical Society. And not long after, he met Georgina and I, and they got married in 1969, and they had now 2 children. In 1972, he moved to the newly formed corporate research laboratories of ESSO, which is nowadays ExxonMobil. And they were initiating research efforts in energy beyond petroleum and chemicals. And there, a very vibrant and intellectually stimulating interdisciplinary group was formed, and Dr. Whittingham discovered the key role that intercalation played in the reversibility of chemical reactions. After a presentation to a committee of the Exxon Board of Directors in New York, they set a team to develop this invention. And as a result, Exxon got the first rechargeable lithium-ion battery in 1973. Then, in the early 80s, he became manager of the Chemical Engineering Technology Division of Exxon Engineering, which at that time was expanding in order to explore synthetic fuels, as such shale oil and coal liquefaction and coal gasification, which nowadays are very, very on the top of the fuel studies. In 1984, he was hired by Schlumberger, and this was the largest worldwide company servicing oil extraction wells. There, he spent 4 years and decided to return to academia in 1988, and he joined the chemistry department of Binghamton, which is the University Estate of New York. And his goal was to introduce material sciences across the curriculum and to emphasize to students that science is essentially interdisciplinary. In 1993, he got funding from the US Department of Energy, and this funding still continues nowadays. He was also appointed as Chief Research Officer at Binghamton for 5 years, after which he was Vice Chair of the Board of Directors of the Research Foundation. And then he founded the Institute for Materials Research and led it until 2018. In 2011, he became director of the Energy Frontier Research Centers from the US Department of Energy. This center comprised some of the leading scientists around the US and enabled a fundamental understanding of the reactions occurring in the lithium battery electrodes. At present, he's a member of the Battery 500 group, whose goal is to enable batteries with an energy density of 500 watts per hour in kilogram. He's also a distinguished professor of chemistry, material science, and engineering at the University of Binghamton, New York, and he also directs the Northeast Center for Chemical Energy Storage in collaboration with the US Department of Energy. In 2019, he got the Nobel Prize in Chemistry for the development of lithium-ion batteries, which may play a crucial role to reduce the climate change and protect our environment. Ladies and gentlemen, please join me in a very warm welcome to Professor Dr. Stanley Whittingham.
Thank you very much for those kind words. What I want to do today is really give you a bit of background on how important chemistry, electrochemistry, and batteries can be in maybe solving some of our climate issues. But let me again thank the US Department of Energy. They've supported me for a long time. They've encouraged me in this area, and I take a leadership position with these days. But I want to thank you all for inviting me here. I think it's been 2 years since we've been trying to get this meeting going. And it's nice to meet in person. And I saw you put on good English weather for me here, so I would feel back at home. Because I haven't been, this is my first trip to Europe since we went to Stockholm almost 3 years ago because of COVID. There are a lot of younger folks here, so I'm going to address much of this to the younger folks. There was a time when there were no computers. The younger folks won't remember that. When I started in this area, when we did solved X-ray structures, we basically did it with hand with a bit of help from a slide rule. But those times have changed. So this was what we call the first disruption. You all have iPhones or Samsungs or some equivalent on your body, and there's probably not a single person in this room who does not have a lithium battery of one sort or another on them. Probably seldom we have 2 or 3. So I had to give a short talk at the banquet in Stockholm, and I had to ask now, does anybody not have a lithium battery on them? The only people who didn't was the royal family, because they don't carry the gadgets with them, but everybody else did. So the message you want to get across now, we've done a lot already, done a lot of fundamental science, and as the Nobel Committee said, we've built the foundation. Now we've got to actually build on that and make things happen, okay? So I don't think I need to say too much. You've all seen all the issues of what climate change has done to us, whether it's floods in Germany, and you had a flood in Valencia a couple of days ago, and this is where this picture came from. We had this storm in Fort Myers, Florida, just a month ago that basically wiped out that town. If you've been to Canada and looked at glaciers, and the same with the glaciers, I think in Switzerland, 10 years ago, there were glaciers everywhere. Now this one in Banff, Canada is essentially gone. So they're retreating, and we've got fires everywhere. So this is not an American issue or a European issue, it's a worldwide issue, and we have to start addressing it. So let me mention these, what we call disruptions in humanity. We've had several of them. The first one was what I call a communications disruption. When I was brought up, no, you read the newspaper. But if you're in Australia, it might take you a month or two to find out what was going on in Europe. And if you wanted a scientific journal, it went by ship. So the top Australians came to Europe for a year or two so they'd catch up with what's going on. Now everything's instantaneous. You know what happened in Ukraine, probably when that rocket hit the ground, probably within 15 minutes it hit the ground, everybody knew. That didn't used to be the case. So that was enabled by the lithium batteries. It's mostly positive. The last 3 years, we've had COVID, which has been a negative disruption. It taught us one big thing: we cannot rely on global supply chains. No, we can't have any one country controlling the majority of a single market. But it's also taught us that we as humans, we can react very fast. So it did not take us long to generate vaccines. In fact, it took a surprisingly short time. But we now have to adapt to climate change. I don't think we can roll it back, but maybe we can stop it getting still worse. So in order to do that, we've got to cut out fossil fuels, initially cut out all the coal. No, I know there's issues in Europe right now, so some of the coal plants are coming back on. But we have to do less with fossil fuels. And we're very happy to say in New York State, we don't generate a single kilowatt hour of electricity using using coal anymore. We still use natural gas. Put that in perspective, in my town, in about 2010, they put a small lithium battery facility in place, and I'll show you a picture of it shortly. Within 1 month, they turned off the coal power plant and it never got turned back on again. So a small lithium battery storage can replace a peaker power plant rather easily. But if we're going to go to clean energy, particularly if it's wind or solar, no. There's no sun here today, so you wouldn't get too much energy, so you'd have to get it from some source, and therefore we have to store it. In Binghamton, we have no wind, we have enough sun. So we need to store that energy. The best way of doing that today is lithium batteries, but it's by no means the largest method of doing that. We've all seen the typical method used 10 years ago, 50 years ago, is pumped hydro. Wherever you've got hills, you can use pumped hydro, so at nighttime when there's excess electricity, you can pump it up the hill and then use it in the peak times, say lunchtime or dinner time. And nowadays, you'll be using it to store solar energy. These are remarkably efficient. So you pump the water up, then generate power when it comes down. You get 73% of that power back again. There's very few devices that are that efficient. But the challenge is there's limited new sites, and most countries, or most people in most countries, don't want to have new facilities built in their backyard. Okay? So I know in Britain, they hide them inside mountains so you can't see them. What they're doing in the United States mostly now is making the present ones more efficient by putting new motors and so on in there. But batteries are particularly effective. You can have them tiny ones, which may be in your credit card, or you can have them gigawatt hour size. So they're extremely fast on off, very flexible. Everybody uses them. Unlike the power plants, all the pumped hydro, they take several minutes to turn on and off. Now I show you just a typical example here. This is a facility about 50 miles from where I live, halfway between my town and Albany, the capital of New York State. So going back 50 years, so we built the first lithium-ion battery in 1972. We think about October, November. We're still trying to find the old lab notebooks will describe it. They're in the archive somewhere. But we built those 72. We filed the patents in 73. And in those days, you could play games and delay the issuance of the patents for years and years. So the actual patent, I think, issued about 1977. And that's a copy of it. We built two kinds of batteries in those days, small ones, as shown here in this little device at the top right. This is a paperweight we used to give away to potential customers. It has a solar cell in it and a battery in it and the clock. This particular one still sits on my desk. It's still working. and we think it was built about 1976. So a good lithium-ion battery will last forever. But you could not afford to use these today. This was welded, sealed, so no air could ever get into it. Beneath that are much larger cells. These are about 6 inches by 4 inches, about an inch thick, and these were designed for electric vehicles. That time, Exxon was very interested in getting into electric vehicle business. They got into electric motors for the vehicles. Remember then, we didn't have any gadgets. There was no phones, no music players. We didn't have any of those things back in the 1970s. So that particular large batteries, those were taken to an electric vehicle show in Chicago in 1977 and turned a motorcycle headlamp on and off all week long. And the chefs amongst you will notice those little pressure release valves on top. The solvents were used, tended to gas a little bit. So after everybody went home at 5 o'clock in the evening, we'd release the pressure inside and have them ready for the next day's work. So that's where we were in mid-1970s. This is where we are today. These are the typical electric vehicles you can buy. And I'm assuming there's a fair number of these around here. So we have the little one there, which is 2-seater. That's my wife in it. This is one we rented in Bermuda. If any of you have been to Bermuda, you'll know tourists are not allowed to drive cars. Only mopeds. Well, we said we're too old to drive mopeds. But they said we've now just got new electric vehicles and tourists are allowed to drive those. So we drove this particular one. They told us, if you go to the other end of the island, make sure you recharge it before you come back. Otherwise, you'll run out of battery life. So we drove to the other end of the island, went to the recharging station, and they were still building it. So we hunted around, and part way back, we found a hotel that had a small recharging station. They partially recharged it whilst we had dinner, and we managed to get back. But my wife still has range anxiety. She didn't want to push this car back to the hotel. So this is an issue that's still there. To the right of that are 2 trucks. These were from Pacor. It's Peterbilt and a couple of other companies. In Washington State, just north of Seattle, they have their test facility and test tracks. So I got to drive these around their test tracks. This large, what we call 16-wheeler, is now in the Los Angeles docks, and it transports the large boxes from the ship to distribution points. And the one on the right is a garbage truck. And this is a typical, obvious use for electric vehicles. It's stop, start, raise, lower all day long. So it's very efficient, very clean to be in your environments. Below that are 2 buses, a Mercedes bus, and a BAE Systems bus. This particular bus is electrified in Binghamton, where I live. You'll see on there also a forklift truck. This is also made in the Binghamton area by Raymond Corporation, which is part of Toyota. And beneath that is a very nice BMW car, if you can afford it. So that's where we are on transportation. If we talk about renewable energy, as I said, you have to store it. The one facility in the middle at the bottom there is the largest lithium battery storage facility in the world by a factor of 4. So this is 1.6 gigawatt hours. It's about 1.5 hours south of San Francisco. It's planned to expand to 5 to 6 gigawatt hours in the next few years. Even today, it's not big enough to take the excess solar energy generated in the middle of the day in that region of California. But it has shown the success. They're making money. Next to that on the bottom is this small facility I mentioned in Binghamton. It was built about 2009, 2010. I show you a picture there in 2011, just before we had what we call the flood of the millennium. Binghamton's in the valley, so we had a hurricane that decided to just sit on top of the town and flood us out. Those containers floated nicely. They fixed them up, and they're now in the state of Ohio because they could make more money there. They solved the problems in Binghamton. Above that is a wind farm in West Virginia. Again, a large lithium storage facility, both to shift the energy, but also to smooth it. because the wind is up and down continuously, but it has to be smooth before it goes on to the grid. A third application, which you may not be so familiar with, whilst we're in Stockholm for the Nobel Prize, two of the physicists and I talked to these two astronauts. And what's amazing, you talked to them, they responded immediately. And there was not this delay you remember from the old days with these phone systems. So they just spent the last 2 weeks replacing all the nickel metal hydride batteries on the International Space Station with lithium-ion batteries. They're very happy. They're half the weight, half the size, and we're going to last twice as long. So the space station is now totally lithium-ion batteries. So just in case there's any of you who don't know what a lithium-ion battery is, any battery really has three major components: an anode, which when it's charged in this case is where the lithium would be, a cathode where the lithium is going to go when you discharge it, then the electrolyte that sits in between. So when we started out in SO in 1972, we used pure lithium metal as the anode. No, this was the obvious, cleanest way to go, but if any of you have done electrode deposition, you'll know metals tend to plate in the dendritic form, so you form dendrites that short the cell out. So what we did, we switched over to aluminum metal, so lithium reacts with aluminum 1-to-1 at room temperature. And that worked well for maybe 10, 20 recharges, clearly not viable long term. So it's Akira Yoshino in Japan who really developed graphite-based carbons to store the lithium. Now, the picture shown here is the graphite anode. You can see the sheets of graphite, lithium between it. It works very well. That hasn't changed since the late 1980s. Same graphite we use today as used then, part of it's synthetic, part's natural. The big issue is you need 72 grams of graphite to store 7 grams of lithium. And the graphite takes up half the volume of the cell. So if we want to increase the energy density, we've got to get rid of that graphite. So there's a lot of work now trying to go back to pure lithium, but as an intermediate, we and others are looking at tin and silicon. I know there's a number of folks in this region also looking at silicon as a potential anode. Tin and silicon react with 4 lithium ions each. So on a volumetric basis, they're as good as using pure lithium metal. So a big push there. On the cathode side, which is where the lithium goes, again, we're looking at what we call layer structures mostly. These are what we call intercalation compounds. So same as graphite. You've got a host material where you're going to store the lithium. That host material is not going to change crystal structure. And that's why you can take the lithium in and out thousands of times. It may expand 5 or 10%, but that's all. So we start out with titanium disulfide, and I won't go into the history of that, but no, we're interested in superconductors, and tantalum disulfide was a superconductor. If you put electron donors into it like lithium, potassium, you could change its superconducting properties. But obviously we're not going to use tantalum in the battery, so we switched to titanium disulfide. It's the lightest, but has another huge positive trait. It's a metallic conductor. So remember, in the battery, you're putting ions in, you're also putting electrons in or out, so you've got to have conductivity for the electrons. So it had a huge positive effect. It worked very well, but its voltage was about 2 to 2.5 volts. When we then combined that with a graphite anode, that cut it down by about another 0.5 volt. So it was John Goodenough, who was then at Oxford. He was chair of inorganic chemistry. He was working on the magnetic behavior of lithium cobalt oxides. He read our paper and said, hey, these compounds have got the same structure. I'm going to try it as a battery cathode. Well, no self-respecting chemist would ever try it. You know, if you took lithium out of lithium cobalt oxide, you land up with cobalt 4+. But if you read all the textbooks, cobalt 4+ doesn't exist. So why even try it? You know? I think these days we know we can make what we call metastable compounds which you cannot make by normal high temperature methods. So he tried it, it works very well. And if you've got an iPhone or any smartphone, any small device, the cathode is still lithium cobalt oxide. But the cobalt is far too expensive. Most of it comes from the Congo, and half of what comes from the Congo uses child labor. So there's a huge push to get cobalt out of the batteries, and so the most common lead compounds used today are mixtures known as NMC or NCA. That just means nickel, manganese, cobalt, or nickel, cobalt, aluminum. So we're trying to reduce the cobalt in there. So they work very well, but cobalt and nickel are expensive, so you'd like to go to lower cost materials. And John Goodenough again found that these lithium iron phosphates, which are naturally occurring minerals, you move the lithium in and out of those as well. As you'll see in a moment, the energy density of those are very poor. So what we've been looking at recently is, can we increase the energy density by putting 2 lithium ions into a structure, or we could put 1 magnesium or 1 calcium. So we've been working at vanadium phosphates. Vanadium can go from vanadium 5 to vanadium 4 to vanadium 3 with no problems. So let's just look at these number issues. Oh, don't worry about the numbers themselves, just look in that red box and you'll see what we get out of a commercial cell today is somewhere between 11% and 25% of its theoretical volumetric energy density. On the far right-hand side, you can see if you do it on a weight basis, it's round about 25%. So there's still a huge opportunity of increasing the stored energy density. But we've got to get rid of that graphite, which I mentioned, which takes up half the volume and much of the weight. And we've got to get more lithium in there. And the other thing we have to do is make those lithium ions move faster in the materials. If we do that, we can make the materials thicker, then we can get rid of more of the dead weight, the separators, the current collectors, and so on. So that's what we've been pushing, and the major project we have to do that is what we call a Battery 500 project. It's a US Department of Energy effort, and the goal there is to get that weight percentage up to 50%. And I should say, the weight isn't all that important for electric vehicles, really volume. So we keep telling them they should call it Battery 1000. But that doesn't go down so well in political circles. The politicians know all about the Indianapolis 500 race. The happiest if we call this the Battery 500 race. We're going to get there. Okay. So where are we on that project? We're 5 years into it. In this project, we're using lithium metal again. We're going back to where we started out. Mostly on this project, we're using ether-based electrolytes. This is where Exxon worked originally, and you've done electroplating will know that the ether-based electrolytes plate out metals much better than the safe, stable carbonate electrolytes that are used with the graphite anode. We can't easily use ether-based electrolytes with graphite anode because they solvate the lithium ions and they go into the graphite, the solvent plus the lithium, so it swells the graphite enormously. So the typical materials we use have this what we call meatball morphology. I've shown you at the top right there. So the primary particles are a couple of 100 nanometers in size. Those secondary particles are about 10 microns, and those pack very well. And the results we've obtained are shown in the bottom there, and these are mostly done by my ex-student, Jay Xiao, who's at Pacific Northwest National Lab. And you can see in our first year in 2017, we could cycle these batteries about 50 times before they lost all the capacity, in other words, before they died. A year later, we'd got up well over 200. The year after that, we raised the energy density from 300 to 350, and today we're about 1,000 cycles at 350. So we've shown, we can do it, and right now we're pushing towards the target of 400 or 500 watt-hours per kilogram. So how do we get higher? First thing is what we have to do, as I mentioned, we want to get the cobalt out, but the other big advantage of getting the cobalt out, we can increase the nickel content. And if you look at the bottom of that plot there, which shows the discharge capacity as a function of the nickel content, you can see the discharge capacity goes up with the nickel content. But you also see now looking at the left axis that the thermal stability of these materials goes down drastically as we increase the nickel content. As I mentioned, talking about lithium cobalt oxide, these are not stable materials, they're metastable. None of these metals likes to be 4+. So if you heat them up, they will lose oxygen. So you can see the highest nickel one there will lose oxygen at 220 degrees centigrade. We're never going to take the batteries to those temperatures, but that's a direct measure of how reactive these materials are with the organic solvents. So the lower the thermal stability, the more reactive they are. So our goal is to increase the stability of these materials, get the energy density as high as we can, and get the capacity retention as long as we can. And on the bottom right-hand plot is exactly the same plot for different charging voltages, different compositions, but the common thing in there, it all depends on the nickel content. So let's just look at what our options are to reduce the reactivity of these materials. As I say, we want to get as much nickel in as possible so they can be very reactive. One thing to do is decrease the surface area. So the less surface area you have, the less reactive it will be. One option there is to go all the way to single crystals, away from those meatballs. Second way is to actually modify the materials so they're not so reactive. And by that, we don't mean we're going to change the thermodynamics, we're going to change the kinetics. So those oxygen ions cannot diffuse to the surface and be evolved there. This will also reduce what we call the first cycle loss, and I'll show you what I mean by that in a moment. We're doing bulk substitution as well as coatings on the surface, and our goal in the end is to get that energy density as high as we can without damaging the stability. So let's go back to where we started in the 1970s. Titanium disulfide, we used large single crystals. These were single crystals you could see with your eye. You know, you didn't have to put them in the microscope, even though this is a microscopic picture. So some of these single crystals were several millimeters in size, and they reacted very well. Sony, when they built lithium cobalt oxide, they wanted to make lithium cobalt oxide as big as they could to increase the safety. But then when people wanted high rates, they went to these meatball morphologies, as I show you here for what we call 622. That just means 60% nickel, 20% manganese, 20% cobalt. And the latest push, I say, let's go back to single crystals and see if we can make them more stable. And this is a picture that Jeff Dahn has, which is 50% nickel. So the goal is to go back to single crystals, make those work, and if we can make the single crystals work, Jeff Dahn claims we can make the cars go 1 million miles. I don't think any of you are going to drive 1 million miles, but what this means is you can attach your car to the grid at all times when your car isn't actually moving. So your electric utility can take electricity out of your battery when they need it, put it back into your battery when they don't need it. This will stabilize the grid, and if you have a power outage, it will keep your home going for several days. So that's the goal, to interface the vehicle with the grid. And right now, I think there's only one car company that says you can do that without voiding the warranty, and that's Ford with their new pickup truck. But most of the others don't let you do that, but that's going to be the wave of the future. What we're working on now is what's the best size of those single crystals. And say Jay, my ex-student, is saying keep them about 2 to 3 microns in size. They'll work very well, and they won't crack. And I'll come back to this cracking at the moment, in a moment or two. So let's first look at what we can do to increase the energy density of our present materials. So we get one of these materials, and this is an 80% nickel. I show you a charging curve, so we start out about 3 volts, charge it up to 4.5 volts going up that curve. We discharge it, and you can see we never get that last 10–15% of the lithium back into that structure. This is what we call the first cycle loss. That's at about 3.5 volts. This is critical, so that's where the most stable electrolyte position is, because we don't want to push the voltage too high. So we've been trying to understand what's going on, why that isn't possible at the moment. And so what we did is measure the diffusion coefficient of the lithium in these materials. So the solid circles is diffusion coefficient of the lithium going into the materials, and the open circle is just the lithium coming out. And you can see we fall off a cliff at about 70% of the lithium in the material. And this is due to the diffusion mechanism in these materials. It's a vacancy mechanism, and it turns out you need 2 vacancies next to each other for the lithium ion to diffuse very fast. And the best ways to understand that is just look around you. Every aisle seat is full. If another person comes in, all of you have to move to fill those empty seats in the middle. And that's exactly what happens in these lithium materials. So to get the last 20–30% of the lithium in there, all the other ions have to move. And that's why it slows down dramatically. So what we decided, if that's really the case, if we raise the temperature, we shouldn't get such a loss, or if we doped it or substituted it in some manner. So I show you in the center plot there, the effect of going to higher and higher charging voltage. We can get more lithium out, but you can see we still have this issue with the first cycle loss. And you'll see that flat part at the bottom there, we discharge at 2.8 volts, then we hold it there for 4 hours. So you can see we're getting some of the lithium back in. On the right-hand side, we've raised the temperature from room temperature to 45 degrees centigrade, and you can see that first cycle loss has been drastically reduced, which says this is a kinetic phenomena. So let's just look at what we can do to solve that. And the first clue you get, if you look at lithium cobalt oxide itself, it does not have that problem, which tells us if we modify our materials to make them more like lithium cobalt oxide, we should eliminate it. So I just show you 2 plots on the right-hand side, the 80% material and the pure lithium cobalt oxide. The black curve is at room temperature. We've now reduced, when we discharge it 2.8 volts, we hold it for 100 hours. You can see we get all the lithium back in. At 45 degrees centigrade, it all comes back in. Lithium cobalt oxide, it all comes back in at room temperature. So we've said, let's modify an MC, and the technique we used was niobium. So what we did is take our meatballs, we then immerse them in a solution of a lithium niobium ethoxide. So soak in, then we fire these meatballs up. Depending on the temperature we fire at, we can get a coating on the outside, or niobium goes inside the structure. And you can see from that plot there, just 1% niobium, we can eliminate half this first cycle loss at room temperature. As we do the characterization of these materials, it turns out much more complicated. It's not a simple coating. Some of the niobium goes into the lattice, ejects some of the manganese, so our actual coating is a mixed lithium niobium manganese oxide. So we're still doing more studies to understand that. But this is showing what a coating can do. If we fire this material up, so we get more of a substitution occurring. You can see on the plot to the right there, the purple line is, I think, 2% niobium in this lattice. We've got 200 cycles there. We have not lost any of the capacity whatsoever in 200 cycles. So it's really stabilized that lattice. And what we found out, the way it stabilizes it, it stops the cracking of the materials. So remember, even in these layered materials, they expand by maybe 5 or 10%. We've got some of the crystals this way, some this way, if they expand, they then crack those meatballs. And you can see on the plot there with no niobium, big cracks. On the right-hand side there, without niobium, the cracks are much, much smaller. So we're actually preventing the cracking of those meatballs. And this is with a standard LiPF6 organic carbonate electrolyte. It turns out if we switch now to an ether-based electrolyte, you can see we've got 100% coulombic efficiency, and we've got no capacity loss essentially over the first 300 cycles. So we're researching both the material itself and the electrolyte we're working with. Let's switch away from the NMCs for a moment. As I mentioned, we started out with titanium disulfide. Moly Energy in British Columbia, in Canada, switched and used molybdenum disulfide in place of titanium because this is molybdenite which they can dig out of the ground in British Columbia. So they, in fact, commercialized that, built up an industry based on that, but then they had some other issues later on. As I mentioned, then Goodenough developed lithium cobalt oxide, so we went there. Then we went to lithium iron phosphate, and that's the structure of lithium iron phosphate, a nice tunnel structure, three-dimensional structure, so much more stable than the layered oxides. It does not lose oxygen. And you can see there some cycling of this lithium iron phosphate, essentially no capacity loss, no first cycle loss, even though it's a one-dimensional lattice. So our interest now is, can we get the energy density of this material up to compete with the NMCs? One way of doing that is to change out the iron to manganese, so you go from 3.5 to 4 volts. And this is what our colleagues are doing across the street from us in Endicott, New York. They've just started up a gigafactory to make lithium manganese phosphate rechargeable batteries. But the challenge with these materials, you can see that's a nice flat plateau, which may be good for electronic devices, but it's awful to tell, are you 90% empty or 90% full? So you can't tell where you are on that curve. And if you read Tesla's operator's manual, some of their cars have this battery in them now. They say when you get home every night, plug it in, because you don't know whether you're empty or full. So one of the things we're trying to do in the lab is, can we make that discharge curve slightly slopey, even if it's only 300 millivolts, so you know where you are. But our real goal is to modify this material, look at other phosphates, and see if we can't get the energy density up. And we've been working, let's say, using vanadium. And vanadium, again, is a nice three-dimensional lattice, so it's very stable chemically. And after students struggled for a few years now, we as faculty have to remember, we have the easy job, we sit behind the desk. So students just sit in the lab and struggle year after year trying to make the material and trying to make a material that will work. So we made these vanadium phosphates using what we call a hydrothermal solver thermal approach. The advantage of that, we do it about 200 degrees centigrade. It's easy to do in the lab. It's also commercially viable because that's the waste heat in the chemical plant or refinery, so it doesn't cost you anything. So what they did was dissolve all the reactants in basically ethanol with a few percent of water so it didn't reduce too far. Heated this up to about 180 to 200 degrees centigrade, typically for 3 days. 3 days is Friday to a Monday, so they could leave it over the weekend. But we found, you can do it probably in 24 hours. But if you do it for 3 days, the structure comes out very nicely. And what we get now is this vanadium phosphate with 2 protons in the lattice. So if we heat that up, we can drive the protons out, or we can, in fact, build an electrochemical cell and charge it and pull the protons out that way. So what we end up with are these little cuboids. They're about 100 to 200 nanometers in size. And when we cycle those, we get the typical curves shown here. You can see the 4-volt plateau is vanadium 5 to vanadium 4, and the 2.5-volt plateau is the vanadium 4 to vanadium 3. And if you look closely, the black curve is the first cycle, first time we put lithium in and out, and the purple one's the 50th cycle. And you can see The 50th cycle is in fact better than the first one. So we've shown that these materials are stable, that you can in fact find host lattices where you can stuff it full of 2 lithium ions. We're trying to do the same thing with sodium now, so we can get the energy density up. And if we get this working perfectly, it will have the same energy density as those layered oxides and be much safer. Let me just address something. There's been a lot of hype, and I should warn everybody here, don't believe what you read in the popular press. Even if it's a Spanish newspaper, they're no better than New York Times or the London Times or anybody else. A lot of companies have a lot of hype, and it's not clear they've really done the evaluation, or they're not hyping to get more money. So the question has always been, solid-state batteries are safer than liquid ones, because the liquid electrolytes will boil and catch fire and burn and so on and so forth. For maybe 10 years now, we've had these small electric vehicles on the market. They're built by Blue Solutions, Bolloré in France. This came out of Canada. These little cars you can rent by the hour. I think that you can't rent them in Paris anymore because people left them in the street, just to like leave the little bicycles in the street now, but cars block the streets more than bicycles do. So they banned them there. But these particular ones are from Indianapolis. They've been around for a long time with no problems. And Michel Armand, who works not too far from here in the Basque Country at your battery facility there, he makes the comments that in Paris, the ruffians frequently burn the cars when they get upset with things, but the batteries are still good after the car's burnt down. I'm not sure it's quite that way, because there's been a number of issues in the last year or so which questions whether large solid-state batteries are safer. So I show you here a nice Mercedes bus. This has an all solid-state battery in it, lithium metal, polyethylene oxide, lithium iron phosphate. At the bottom there is a garage in Stuttgart, I think from last October. At night, one of these buses apparently caught fire. It burnt down the garage and 25 other buses. So that's the first sign that maybe there are some issues there. They're still doing the official, shall we say, study detective work as to what went wrong. They have a suspicion that the lithium actually melted. They got it so over hot. So that's the first instance. Then in Paris this spring, 2 buses using the same batteries but built now by Bolloré itself caught fire whilst in service. No one got hurt, everybody got out in time. Most electric vehicles are built in such a way that you've got at least 10 minutes warning of things going wrong so you can get out. Teslas are built that way, I think these buses are as well. But these buses are now out of service. I don't want to over-dramatize this, but whenever you store energy, it's going to try to release that energy. So inherently, energy is unsafe. Show you several pictures here. These are these 2-wheelers in India. A lot of those caught fire. They had but at very low cost, poorly protected batteries in them. So all your lithium battery devices have a huge amount of electronic protection in them to stop things going wrong. But many of these cases, if you buy a cheap battery, particularly if you buy it from certain countries in the world, it may have the electronic protection in there, but our experience will be it may not be connected. So if you X-ray it, it looks like it's there, but it's in fact not there. So that shows the example there. The picture on the bottom there, in the middle on the right, are 2 vehicles. The middle one is an electric vehicle, and the one on the right is a 120,000 euro car built by Nissan, a sports car, internal combustion engine, and if you looked at them, you couldn't tell which is which. And the one on the right, what they did, they went for a hike, left the car on top of some dry leaves, and the catalytic converter set the dry leaves on fire, then the whole car burnt away. And in the United States, there's about 300 people die every year from gasoline fires, not in an accident, just where the gasoline tanks caught fire in normal motion. So we've accepted that. In many cases, it's not the battery's fault, it's the electronics fault or other fault. So the storage facility there, I think it's from Australia. It was a coolant leak inside the system that shorted out one of the batteries. And quite often it's the actual power electronics that shorts the batteries out that causes issues with the batteries, not the batteries themselves. So let me just conclude with a few comments. The future for greener, safer energy is going to rely on electrochemistry, so I hope there's some electrochemists here. Now, it's important. These what I call lithium intercalation batteries. That intercalation just means we're putting a guest into a host and taking it back out again. They're going to dominate for the next 5 to 10 years, partly because there's nothing that's technically better today. But even though there's something technically better, it's got to get its cost reduced below lithium ion to break into the market. What we really need today, though, is new manufacturing technologies. So, no, I'm a fundamental scientist, or I was for a long time. We've got to take our inventions and convert it to the marketplace. So there's no point in us coming out with a brand new material unless we tell folks, here's how you can make a ton of this material, not 5 grams of it. Right now, most of the material used in the batteries, all these oxides, NMC, are made by batch processes, even by the industrial giants. They're not a continuous process. The real goal, if we're to move forward, is we have to leapfrog the Asian technology. The Asian technology is now 30 years old. It really hasn't changed, which means we'd like to get a lot of the bad stuff out, the NMPs, which are the organics we use to make the paste to make the electrodes. We need to get those out and find cleaner methods of doing it. We've got to, in the mining process, get away from carbothermal, where we make all the CO2. We can use clean energy and then use electricity to do electro-reduction. We also need to recycle everything. And I don't know if Spain's any better or worse than the United States, but most of your old cell phones and computers are probably in your top drawer or in the basement of your house or somewhere. They all need to be recycled. There's a lot of cobalt in there. They're valuable to the recyclers, and they can go into new cars. The other interesting areas, can we make clean hydrogen in an economically viable method? And I know there's a shift now of thinking hydrogen may not be the way to go. Maybe ammonia is a more efficient way to go. So there's a lot of work there. And the key thing we have to have, and I'll mention this on the next slide, we need regional supply chains. Europe started this maybe 4 or 5 years ago. So they're ahead of us. And the big push is what we want, and I expect all of you want. We want to be able to say, these batteries, these devices are made in America or made in Europe. We're not importing them all with all the transportation and the other issues. And we want a clean ecosystem. So let's just quickly look at the global supply chain. The present supply chain is untenable. It's insecure, it's not sustainable. Some of these battery materials, from the mine to the finished product, they travel between 30 and 50,000 miles, which is crazy. It takes between 60 and 80 kilowatt hours of energy to make a 1 kilowatt hour battery. We have to reduce that. We have to do better science to eliminate the critical elements like cobalt, take those out. To put an example of the present situation, the US has now opened up a mine in Idaho. It's a small mine, but the processing of that material is either done in Finland or in Brazil. Not in the US, not in Canada. No, it's crazy, but that's the way it is. Things like graphite and the other metals, we should be able to resource locally. Now, I know in Europe there's a big push to get most of the mining done in Scandinavia using clean hydro energy, then build the batteries in Germany, Spain, or Hungary and other places, but keep it all within the region. So in the United States, and I think I've convinced the federal government of the United States to stop talking about US. We're a continent. We've got to work with our Canadian colleagues. Our Canadian colleagues have tons of clean energy. They have lots of nickel, a lot of graphite, and other materials. So we're working with them. We have a huge amount of battery R&D effort in the universities there. Huge number of startup companies are pushing this, but they come with exponential hype, so you have to read between the lines as to what they actually have. And I know there's a number of large institutions in Europe, including in Spain, doing similar things. But for the students, if you look up any patents on chemistry in batteries, they're all either American or European. There's non-Asian. All the Asian know-how is in the engineering of it. Okay. So we have a big issue in North America. We can make good ideas. How do we get that good idea into the market? So we have to find a way of prototyping batteries and then actually making battery equipment. Most of the battery equipment used in the world comes from Asia. A lot of it comes from South Korea. Not too much from Japan, because Japan's too expensive. And these days, obviously, in the US, I don't know about Europe, we don't bring anything in from China. Okay? But changes are coming. There's a huge amount of US federal funding coming into the United States. I'd say it's about 3 to 5 years behind Europe. You've had a EU battery effort of several billion euros for about 2 or 3 years now, pushing this. So we have a big program just started up, and for those who want to hear more about it, come tomorrow evening to the public lecture and I'll fill it in. So this project officially started about 2 weeks ago. On the left-hand side, I'm explaining to Undersecretary of the Economic Development Agency, they're the ones who are funding this, about how big batteries are, and this is in our gigafactory, which is just starting up. On the right-hand side, if any of you know American politics, you'll recognize Senator Schumer, who leads the Senate in Washington, D.C. He was at Binghamton also for the opening of this effort, and I'm sure he's a very happy man now, because he's now going to lead the Senate for another 2 years. So we'll keep this effort going. As I said, I'll talk more about this tomorrow night. I want to get back to really, we need regional activities in everything we do. Now, each region in the world needs to be more self-sufficient, and they need to be more responsible. So we've seen issues with energy storage. I've talked about that. It's exactly the same thing with semiconductors. When COVID started, where did most of you get your masks from, if you could get them? Real difficult. They came from China. I was lucky. I had many ex-Chinese students, and they'd email me, how many masks do you want this week? And they'd send a box full of them over. But no, that's not a tenable situation. I think we learned from that. So we have to regionalize things more. It's fine if one area makes 30 or 40% or something, but when they make 90% or something, we have problems. So we've got to also emphasize sustainability. We've got to recycle everything, and within the region. And I want to make the point that, and I think some people are getting on board, we, the developed nations, we have to be responsible for everything we make. And if we make plastics, we have to recycle it, not ship them off to a third world country and then dump it on them. This applies to plastics, clothing, electronics, and everything else. So I want to push regional, and I heard in my talks this morning we're trying to do a lot of things here, and I encourage you to keep going, and I'll be happy to take any questions you've got them. Thank you very much.
Question? I have one. If I understood correctly, you said that lithium-ion batteries could be like living forever?
Yes.
This is a bit curious because all batteries are dying nowadays in the mobile phones or whatever.
Right. So it depends how much you're willing to pay. So the batteries we made in the 1970s, we used glass seals, welding, very expensive, and they'll last forever. Are you willing to pay for a battery that lasts 20 years in your smartphone when you're going to replace the smartphone in 3 or 4 years? So those batteries are really designed to last 3 or 4 years. If it's in the cars, it can last 8 to 10 years. For grid storage, they want 15 to 25 years.
So they are prepared by design, more or less.
I would say to some extent, don't think of it negatively then. To make it last longer, you've got to have thicker separators, thicker current collectors, so you have less energy in a given volume or weight, but it will last longer. So it's a trade-off.
Some other question?
Yeah.
More than a question, it's a curiosity for these big battery factories that store energy, for how long they can store this energy? For how long?
Oh, there's two parts. How long can they store it? No, on a day or a week?
Yeah.
That's all economics. If you recycle it every day, you get your money back quicker. But if you store it for a week, then you don't get so much money back. So a lot of the companies now, they buy cheap energy at night time. And there's a facility near Saratoga Springs that's been running for about 5 years now. They started making money within a few weeks. They buy cheap energy, say 1 a.m. to 5 a.m., and they sell it back to the utility at, say, noon or 5 p.m. So it's, no, 24-hour cycle is the most efficient economically. It will last for days or weeks or months, but you can't afford to do that because you'll be capital investment.
So they don't have very large losses?
They should, in theory, there should be no losses in a lithium battery. Right. Yes.
Small question. You talked about a very important aspect of this, about sustainable chemistry, which is trying to limit our technologies, at least resources, within our region, to limit transport and try to adapt. But we know that, at least in Europe, we have a lack of several heavy metals that are more prominent in other regions. Do you think that this will affect the kind of technology we can have in our region? For example, China is Asia is more prominent in certain metals that we don't have. That's why we tend to transport so many technology from there. We can have different types of technology that use the same functions. Like, for example, we have a metal that here is more prevalent, but it's not commonly used in batteries. Can we try to improve technologies to adapt to each region? Is that a possibility? Or a worldwide technology is going to be always the most common thing?
So to emphasize, China does not necessarily have the materials. They import all the materials. Then they process them all in China. So certainly in this area of the world, you've got some nickel up in Scandinavia, you've got lots of iron everywhere. In Morocco, you've got the highest concentration in the world of phosphate. So you could easily make lithium iron phosphate batteries. In Europe, I think there's a couple of the countries, Serbia and Bulgaria and others, have got lithium resources. So that the materials there, and I think if you want them, if you look hard enough, you'll find them. And certainly the largest producer of lithium in the world right now is Australia. And Australia is looking for new markets because most of the lithium is presently going to China, and they'd be happy to sell it to Spain, US, anybody who will take it.